Hi everyone, welcome back to the channel. In our last session, we have given discussion regarding the one important class of organic compounds, that is amines. So with respect to amines, in our last session, we have discussed about the basic introduction followed with the detailed classification of amines. And in this session, we shall give discussion regarding the synthetic methods through which we can prepare amines, in particularly primary and secondary amines, but we give main focus to only primary amines. And in this session, we shall discuss three important methods of preparation of amines. One is called as the reductive amination of carbonyl compounds, and second one is Gabriel phthalimide synthesis, and third one is the reduction of nitroalkanes. So with respect to these three things, we shall give a detailed discussion in this session. So now we shall directly enter into the session. So first we shall go with the synthetic methods. First one is the reductive amination of carbonyl compounds. So this is a first method of preparation of amines. So here we have said reductive amination of carbonyl compounds. So we know that carbonyl compounds, in the sense aldehydes and ketones, what we are going to do, we are performing amination of carbonyl compounds with the method following reduction. So first we aminate the carbonyl compounds, later we do the reduction. Through that we are going to get the amines. This is the simple basic knowledge regarding this heading what I have written on the board. So this is reductive amination of carbonyl compounds. So what we will do in case of reductive amination of carbonyl compounds? So here we will be going with a carbonyl compound. So this is the carbonyl group. Here if you can have an alkyl or aryl group and hydrogen, for which what we calling as aldehyde, or on either of the side you will be having alkyl or aryl group, what we call it as ketone. So that means a carbonyl compound means it can be either aldehyde or it can be ketone. So when an aldehyde or ketone is made to react with ammonia, NH3, in presence of the catalyst, I mean to say we need to perform the reduction in presence of the catalyst NaBH3CN. So we call this as sodium cyanohydridoborate. I repeat, sodium cyanohydridoborate. That is the name of this reducing agent, NaBH3CN. This is sodium cyanohydridoborate is the name of this material. So in presence of sodium cyanohydridoborate, when aldehyde or ketone is aminated followed by reduction, we are going to get amines. This is the basic idea regarding the reductive amination of carbonyl compounds. And now we shall give some simple examples so as to understand how we can obtain amines through reductive amination of carbonyl compounds. So firstly, we shall consider aldehyde, say CH3CHO. We have taken acetaldehyde, or we can simply call it as ethanol. So it is acetaldehyde, or in IUPAC system we have two carbon atoms, so it is ethan, Al is the suffix because it is an aldehyde. So here the aldehyde will be first reacted with ammonia. So here this is a carbonyl compound. When carbonyl compound is made to react with ammonia, first we are going to get an imine like this. This is an imine. And this imine will be subjected to the process of reduction in presence of sodium cyanohydridoborate. So, in presence of sodium cyanohydridoborate, reduction of imine will result in the formation of CH3, CH2, NH2. This is the thing we are going to get. So, acetaldehyde, that is ethanol, is going to produce 2 carbon atoms. So, it is ethanamine. Simply ethylamine is produced. Simple way. Acetaldehyde is first reacted with ammonia, and here there occurs elimination of water molecule. So, acetaldehyde will react with ammonia so as to produce imine. Imine on further reduction in presence of sodium cyanohydridoborate will be producing ethylamine. You can notice which is an primary amine. So, we can go with one more example. Let us consider C6H5 C double bond OH. So, here we have taken benzaldehyde, an aromatic aldehyde, right. So, when benzaldehyde is first reacted with ammonia, it will result in the formation of C6H5 C double bond NH. So, benzyl imine. So, here we got an imine, and this imine will be further reduced in presence of sodium cyanohydridoborate. Reduction of imine will result in the formation of C6H5 CH2 NH2. So, this is benzyl group and it is amine. So, it is benzyl amine. So, here we observe that the conversion of acetaldehyde into ethylamine and benzaldehyde into benzylamine. So, in this way we can easily convert an aldehyde into corresponding primary amine on reaction with ammonia followed with reduction of the resulting imine in presence of sodium cyanohydridoborate. So, these are the examples for which conversion of aldehydes into corresponding amine. Here also you can notice the benzyl amine what we got, it is also a primary amine. So, one point we can observe over here, when aldehydes are subjected to the process of reductive amination, that results in the formation of primary amines. Okay. So, we saw how an aldehyde on subjection to reductive amination will produce primary amine. And now we shall go with the another carbonyl compound, that is ketone. So, we saw that when aldehydes are subjected to reductive amination, it results in the formation of primary amine. And now we shall see, if you subject ketone to reductive amination, whether we are going to get primary amine or secondary amine. So, fine. So, if you consider the ketones upon subjection to reductive amination. So, let me write the general expression for the reductive amination of ketone. So, here we have taken the ketone, and if you subject this ketone to the reaction with ammonia, a ketone on reaction with ammonia with the elimination of 1 unit of water molecule, that results in the formation of obviously an imine, and this imine on reduction with sodium cyanohydridoborate. In presence of sodium cyanohydridoborate, we are going to get RCH, NH2 and R dash. So, that means ketones On reaction with ammonia, first will produce imine, which on further reduction in presence of sodium cyanohydridoborate, we are going to get a secondary amine. So when aldehyde is subjected to reductive amination, we will get a primary amine, and when ketone is subjected to reductive amination, we are going to get a secondary amine. Now we shall see some simple examples for reductive amination of ketones. So firstly, we shall consider CH3, C double bond O, CH3, that is simply nothing but acetone. And if you go with the IUPAC system, totally we are having 3 carbon atoms. So propan is the root word. Second position is carrying the carbonyl group. So the position should be indicated as 2, and the suffix for the ketone is -one. So acetone, that is nothing but propan 2-one on reaction with ammonia with the elimination of 1 unit of water molecule, first results in the formation of an imine. And imine on further reduction in presence of sodium cyanohydridoborate. The imine on reduction with sodium cyanohydridoborate, CH3, CH, CH3, NH2. Nothing but here we are having 2 hydrogen atoms. One hydrogen will comes to this carbon atom, and the another hydrogen will go to the nitrogen atom by forming NH2, and here it is CH. So you can notice over here, totally we are having 3 carbon atoms over here, and the position of the NH2 group is at 2. That means this is the isopropyl group. So we can call this as isopropyl amine in common system. But if you go with the IUPAC system, 1, 2, 3, the second position is carrying the amine group. So it will be propan 2 amine as the IUPAC name of the material. So we can go with one more example. Here we went with aliphatic ketone. We can go with aromatic ketone also. So shall consider an aromatic ketone, COCH3. So this is the aromatic ketone. It is nothing but acetophenone. So when acetophenone on reaction with ammonia, there occurs elimination of water molecule, and that results in the formation of the intermediate, which is called as an imine. So this is an imine, and this imine on further reduction in presence of sodium cyanohydridoborate, 1 hydrogen to the carbon atom and second hydrogen to the nitrogen atom, and that results in the formation of CH, CH3 and NH2. So here also we got a secondary amine. So if you want to give the name for this, 1, numbering should be started from here, 1, 2. The second position is having the benzene ring, and at the second position itself we are having NH2 group. So here this benzene group will be acting as a substituent, so we should call it as 2-phenyl, because this group is present at the second position. So 2-phenyl, and in the aliphatic chain totally we are having 2 carbon atoms, so ethane, and at the second position only we are having NH2, so 2-amine. So here in both the cases we are getting the secondary amines. So in case of aldehydes, reductive amination will result in the formation of primary amines, and in case of ketones, reductive amination will result in the formation of secondary amines. Fine. So till that we said when aldehydes are subjected to reductive amination, we will be getting primary amines, and ketones are subjected to reductive amination, we will be getting secondary amines. One question may comes to our mind: can't we get secondary amines by subjecting aldehydes to reductive amination? The question, for that question, the answer is S. We can get the secondary amines by subjecting aldehydes to reductive amination, but the reaction pathway will be slightly different. How? The thing is, in order to get secondary amines by subjecting aldehydes to reductive amination, so let me consider acetaldehyde itself, CH3CHO. So when acetaldehyde is the reactant material, and if your interest is to get a secondary amine starting with acetaldehyde, instead of reacting with ammonia, we need to react this acetaldehyde with a primary amine. So if you react an acetaldehyde with primary amine, instead of primary amine, we will be getting secondary amine. It's a two short simple strategy. So here we have acetaldehyde. If I take a primary amine, here I have taken methylamine. So when acetaldehyde is made to react with methylamine, same thing, in presence of, okay, first you react with methylamine, you are going to get CH3, C double bond NH, and here you will be getting CH3. So like this you will get, okay. So acetaldehyde on reaction with methylamine, you will be getting a secondary amine. So acetaldehyde on reaction with methylamine in presence of a reducing agent such as nickel or platinum or palladium, or in presence of sodium cyanohydridoborate, instantly we are going to get a secondary amine, and here we got isopropyl amine. So is the easiest way of converting acetaldehyde into a secondary amine, and this is the whole and sole thing about the method that what we followed in order to produce amines, that is reductive amination of carbonyl compounds. Okay, so we have already given one important method for the synthesis of amines, and now we shall go with the second method of synthesizing amines. The most important one is Gabriel phthalimide synthesis. So in this method, what we do is, firstly we consider one phthalimide, and this phthalimide will be reacted with alcoholic potassium hydroxide, or we can take sodium hydroxide also, so that we will be getting potassium phthalimide. And this potassium phthalimide will be further reacted with an alkyl halide, and on reacting with alkyl halide with potassium phthalimide, we will be getting two products. One is phthalic acid and another one is primary amine. So this is the reaction pathway of Gabriel phthalimide synthesis. Phthalimide will be first reacted with alcoholic KOH so as to get potassium phthalimide, which on reaction with alkyl halide we are going to get primary amine as major product along with phthalic acid. So through this method we can prepare only primary amines, and the question number one that comes to our mind is, can't we prepare secondary and tertiary amines through this method? The answer is no. We can't prepare the secondary and tertiary amines through Gabriel phthalimide synthesis. And question number two, here we have taken alkyl halide. So as the primary amine, what we will get over here, it will be an aliphatic primary amine and not aromatic primary amine. That means in case of Gabriel phthalimide synthesis, only aliphatic primary amines can be prepared but not aromatic primary amines. Why? The answer for this question is the Gabriel phthalimide synthesis in production of amine is purely a nucleophilic substitution reaction. So by listening to these things, you can come to know that aryl halides, if you have taken aryl halides over here, I mean to say, in order to produce aromatic primary amine, here you are supposed to take aryl halide. But aryl halides cannot undergo nucleophilic substitution reaction. This is the reason why Gabriel phthalimide synthesis is not suitable for the production of aromatic primary amine, but it is the very best method for the production of aliphatic primary amines. And now we shall go with one simple example so as to explain the Gabriel phthalimide synthesis. So first we need to consider phthalimide. This is phthalimide. So phthalimide has been taken and this is supposed to be reacted with alcoholic KOH. So when you react phthalimide with alcoholic KOH, the hydrogen and hydroxyl group, that means H plus and OH minus will combine and that results in the elimination of water molecule, so that the nitrogen will get the negative charge and this potassium with positive charge will get attached over here so as to get potassium phthalimide. So phthalimide on reaction with alcoholic potassium hydroxide results in the formation of potassium phthalimide. And this potassium phthalimide is supposed to be reacted with an alkyl halide. So let us consider CH3Br. So I have taken methyl bromide, an alkyl halide. So methyl bromide will be reacted with potassium phthalimide. So on reaction of this methyl bromide with potassium phthalimide, here you can notice bromine will be having negative charge over here and carbon will be having positive charge. This negative charge will be donated to the potassium so as to eliminate potassium bromide. And here the negative charge which is there on the nitrogen will be attacked towards the carbon atom of the methyl group. So we will be getting the alkyl substituted phthalimide, and here in this case the methyl substituted phthalimide. So here we got methyl phthalimide. So potassium phthalimide on reaction with methyl bromide with the elimination of potassium bromide, we will be getting the methyl substituted phthalimide, and this on further subjection of hydrolysis either with presence of acid or base. So in presence of base which will be acting as a catalyst, when methyl phthalimide is subjected to the process of hydrolysis, we are going to get two simple products, that is COOH plus this methyl group along with nitrogen will receive the hydrogens so as to produce CH3NH2. That means here we got methyl amine, and this is phthalic acid which is an aromatic dicarboxylic acid. So this is the simplest mechanistic pathway what we can give to Gabriel phthalimide synthesis. By using phthalimide we can prepare the aliphatic primary amine, and here in this case we have prepared methyl amine. So instead of methyl group we can go with ethyl group, isopropyl group, like that we can prepare any one. Okay, so Gabriel phthalimide synthesis is a very best example for the preparation of primary amine. In a strictly speaking way, aliphatic primary amines. And that's about the second method for the production of amines, that is Gabriel phthalimide synthesis. We have finished with the two methods of preparation of amines, and now we shall go with the third method, that is reduction of nitrohydrocarbons. So the name itself telling you reduction. So reduction means we have to add the hydrogen atom. I mean to say we have to hydrogenate the nitrohydrocarbon, and for the process of hydrogenation we can use either platinum or nickel or palladium, or even you can go with lithium aluminum hydride, which is a very strong reducing agent, or else for a best results we can use tin in presence of hydrochloric acid or zinc in presence of hydrochloric acid as best reducing agents in order to reduce the nitrohydrocarbons in order to get the corresponding amines. So by using these things, we shall look over how to convert the nitrohydrocarbons into amines by performing reduction. So let us consider some simple examples. So here I will be considering CH3NO2, that is nitro, one carbon atom is there, so it will be methane. So it is nitromethane. So nitromethane, when subjected to the process of reduction in presence of tin and hydrochloric acid, it results in the formation of CH3NH2 with the expulsion of H2O. So nitromethane on reduction in presence of tin and hydrochloric acid, I am getting a primary amine, that is methyl amine. So similarly, I can go with one more example. This time I will be going with aromatic nitro group, that is nitrobenzene. Nitrobenzene. When nitrobenzene is subjected to the process of reduction in presence of either tin under HCl, or you can go with zinc in presence of hydrochloric acid, we will be getting the reduced form of the nitrobenzene, that is NH2 with the expulsion of H2O. That means nitrobenzene on reduction in presence of tin and HCl or zinc in HCl, or you can use reduction in presence of platinum, palladium or nickel, or you can go with a strong reducing agent such as lithium aluminum hydride, or else you can use these things also so as to get the corresponding amine. And here nitrobenzene is producing aniline, or you can call it as benzene amine. So you can notice over here the nitrohydrocarbons on reduction preferably producing primary amines. So as I told in the very beginning of the video, in this session we will be giving the synthetic methods for amines through which we can produce primary amines in particularly. So these are the things about reduction of nitrohydrocarbons through which we can prepare the primary amines. So in this video we have discussed three methods of production of amines. One is the reductive amination of carbonyl compounds. The second one is the most important one, Gabriel phthalimide synthesis. And thirdly, production of amines through reduction of nitrohydrocarbons. And this is the three methods of production of amines.